I will. Thank you. Recorded and summarized. Formidable. So today I'll talk about, I'm sharing keynotes. That's good. I'm going to talk about partition of unity. Do you see the screen? Anybody does not see the screen? Anybody could yell? Yes. Okay, perfect. Thumbs up. You see the screen, you hear me, it's being recorded, so everything's fine. We have transcripts, transcriptomics, and everything we need. Just RNA is missing, but that's fine. All right, so now we'll do Alt Command P. And so those that I'm showing here are examples of phenomena where it's not so easy to simulate using the standard finite element method that we talked about until now. The first one is the shuttle crash in 2003. Now we know why it happened. It's because there were some tiles of ceramics that got displaced and then led to the overheating and subsequent fracture of the shuttle. On the top right, you have the landslide that's very well known in Colorado, where everything just fell down the road and everything else with it. And you can see cracks that are common on the shuttle crash and the landslide. The third one, bottom left, is a Taiwan earthquake, also in 2003, where the bridge literally fell to pieces. And the fourth one is fragmentation of concrete, which unfortunately could be useful when you try to understand what happens if a building is set into an explosion for some reason that I let you imagine. So in all cases, what you can see is originally there is a continuum. The shuttle is more or less continuum. As far as we know, we look at it from far away. So it looks like a continuous medium. And as soon as the cracks start to develop, you start having discontinuity. So that means that if you were, as I'm doing with the mouse here on the screen at the top left, if you identify in these two disks, you see that if you moved from the bottom of the disk to the top of the disks, at some point, you will need to go through a fault or a discontinuity. So if you were a little ant and you were to walk along down there, you would not be able to cross because there would be a rift, literally some sort of Grand Canyon in the middle of the way. So you would need to go all around and go there and then finally find your way across. So that means that this is essentially a discontinuity. Same thing here. You have a huge gap in the road, and that gap is a jump. Literally a jump, because you have part of the road down here and part of the road up here. At the bottom left, same thing. You very clearly see that the concrete, which used to be continuous, now clearly has a jump that you can see with your naked eye, which is not a good sign. And then finally, this problem here of fragmentation is a bit of a different story. So now the problem here is not so much that you have discontinuities, but that you do not have even a continuum anymore. Because if you start looking at what is going on that fragmentation block, well, what happens is that you start with something which is continuous, and at the end you end up with only fragments. And the way you, in fact, verify and validate methods when you talk about fragmentation is to count the number of fragments of any given size. In other words, you will have a distribution which will show you what is the average number of fragments of size 1 meter, then the average number of fragments of size half a meter, 10 centimeters, 1 centimeter, 1 millimeter, and so on. And that gives you an idea whether your simulation method is able or not able to simulate the process. And in that case, the problem really is that even though you're using a continuum method, what you need to deal with is a discontinuum, because you have so many fragments that the continuum assumption is not easy to verify. In fact, you could even claim that the continuum assumption is not verified, because you end up with a lot of fragments that are not even connected to each other, which goes against the continuum assumption. So what do you do in these cases, which are also represented here? I wanted to show you as many examples as I could, because I think it's always useful to be able to set your mind around an idea. So here is another crack in concrete. Here is the sort of very fashionable convertible aircraft. That's a Comet. This is a type of aircraft that had square windows, and the square windows led to stress concentration. The stress concentration led to cracks, and because all the windows had square angles, the cracks connected to each other and then eventually broke the whole fuselage, which led to this very beautiful, fashionable convertible. You also have to deal with that with reservoir. In oil reservoirs, for example, here you have a shale reservoir, which is also very fashionable. And this is something that you need to figure out when you want to extract CH4, which is natural gas, or methane from the reservoir. So what you do is you try to inject fluid in there in order to open the cracks and increase the flow of gas that you try to recover. And you want to do that in a controlled manner, because that determines the flow rate, and the flow rate is important so that you don't waste CH4, which you actually do. One of my friends from Texas has a very nice paper in Science that shows exactly what happens in real life. And this is actually a bit alarming, because it contributes to a large extent to global warming, because all the oil wells and natural gas wells, they all leak. They are not colmated, they are all leaky. And the CH4, I think the total amounts for approximately 20% of global warming, something of that nature. A lot comes from agriculture, but a lot comes from in the industry as well. So that's why if you want to have applications in real life, discontinuities like fracture are a very nice example. So this is a composite material, which we designed with Limerick in Ireland. And the PhD student that worked with us on that is Lisa Cahill in Limerick. And she worked on this. She tried to simulate and do an experiment of a crack in a material which is supposed to withstand certain loads. This material is not isotropic. That means that certain directions contains carbon fibers that are aligned with, in that case, the 45-degree direction. And as you can see, the crack, instead of running horizontal as it should normally do, because you're pulling vertically on that sheet, the crack is running at a 45-degree angle from both tips, which are the ends of that crack that I'm showing now with the mouse. So the tips of the crack are originally here, and the cracks run along the fiber direction, simply because it's the easiest way that they can propagate. So on the left, you have the numerical solution. On the right, you have the experimental solution. And on the bottom case, you have exactly the same type of problem, except that you have now the hydraulic part in the fracture. So that means that you are subjecting the fracture to load coming from water pressure or bentonite pressure, in that case, that you are pumping into the crack in order to make it open, such that you can extract the gas that is going to escape from these shale deposits. Top right is work that we've done with Cineiro, where you see the propagation of a three-dimensional crack using an error estimate. This is what I was referring to during the previous lectures, that it is highly useful to have an idea how you estimate the error of a simulation, because if you do that, you're able to automatically adapt the discretization, meaning here the size of these tetrahedra to the error that you are committing. So you can see here the tetrahedra are very large, and here they are very small, and we'll come back to that later in this particular lecture. The bottom right is work with Timon Habchuk in Bauhaus Universität Weimar, and what he does there and elsewhere is the fracture of concrete, and he does many other things. He's a very prolific researcher and a very good friend of mine. And what he does is essentially look at concrete under very large loads. This is reinforced concrete. And so simulating concrete in itself, even without reinforcement, is extremely tricky because of the nature of the materials. It's a material that will deform even without any load. So it will deform under its own weight. It is a multi-phase material, so essentially it flows over the years, right? So it becomes stronger, so it becomes stiffer, but it also flows, so it deforms. And that deformation is not easy to take into account, but here we're not even talking about that. We're talking about the complexity of the interface between the rebars, which are these metallic bars that you put in concrete. So you put them there because you want concrete to be able to withstand tensile loads, not only compressive loads. Concrete is extremely good in compression, meaning that you can really push on it like crazy and nothing will happen. It's very difficult to break concrete in compression. It's very easy to break concrete in tension. So if you take a specimen and you pull on it on both sides, what's going to happen is that it's going to break immediately. There is a very small resistance to tensile stresses. And what happens if you have a concrete beam is that you bend it like this. If you see a screen, I'm trying to mimic the bending. So the bending means that at the bottom, you will have tension because everything that's at the bottom will be pulled from each other. You can imagine you take a ruler and you bend it like that. At the top, the fibers will compress together. At the bottom, they will extend. So anything that's at the bottom of a beam, which is under compression or bending in that case, at the bottom, you will have tension. At the top, you'll have compression. Therefore, at the bottom, you will need to put some other material, usually steel, in order to help the concrete be able to withstand the tensile part of the load. And that's very important to understand. And in order to simulate all of that, all these examples, including the fracture and brittle fracture that you see at the bottom right, which is all that sort of, you start with a continuum. This is a Taylor bar hitting a wall at large velocities. This is a way that you measure the ductility of a material. This is very interesting because you see petals that are forming, and the number of petals indicates the ability of your method to reproduce reality. So if you're able to reproduce the fact that you have here 4 petals and 2 minor cracks per petal, well, that's going to show that your method is able to reproduce that. And using computations, we are able to do that. So at the left, you have a ductile fracture, meaning that the material slowly deforms and eventually breaks, but progressively. You see the deformations are huge. On the right, what you see is that the material is brittle or quasi-brittle at least, meaning that you end up with loads of fragments, but these fragments are not continuous anymore with the original structure. So that is why it is very useful to have an idea how you deal with cases where the finite element method is not able to do very well. And what I'm showing here does not make me any younger because it dates back to my PhD, which started in 1999, so 26 years ago. But as a matter of fact, things are still more or less valid today in terms of the methods that we use. So I'm going to use that as an example of how to do things. So the papers you see here are effectively the papers that I published during my PhD in 2006, 7, and so on. Just give me 1 second. I'll come back to you in approximately 1 minute. So you can take a bathroom break if you like. I just need to check something because I have something going on. All right, we are back. So, so I was saying that it's so that takes back to my PhD, and I'm going to explain to you something which I think will make it absolutely transparent why we need what I'm going to teach you today, because I think you probably have not heard of that method yet, at least not in that level of detail. So, my PhD was the following, very simple, at least I thought so. This is an aircraft electrical access door. So that's a Boeing 757 electrical access door. This is made of cast aluminum. It is quite heavy. I had it in my office. I remember having difficulties moving it around. So you can imagine something quite sturdy, quite tough, strong. And their question was, let's use that as an example to come up with a completely new method to predict the durability of aircraft components. The question is, in the FAA, which is the Federal Aviation Administration, but also in Europe and everywhere in the world, you have norms that you use in order to design things. And the way you do things today is called damage tolerant design. So the way you do things is that you assume that every component could already be flawed, meaning that a crack may already exist in the component as the life of the aircraft starts. What does that mean? It means that no component is pristine. No component is not flawed. You always assume an initial crack, and the way you assume it is that you put it in the worst possible place in the component. So you put it where the stresses, in particular the tensile stresses I was talking about earlier, which are the stresses that open things up, because this is what is going to open the crack. If you take a piece of paper and you make a little crack and you pull on it, this is going to open the crack. It's going to get longer. It's going to, simply grow. Now, if you compress it, it may grow in certain cases, but in general, it won't grow. So cracks grow under tension. So you're going to look for the places, the locations in that component where the stresses are, in terms of tensile stresses, the highest. So you look for the maximum principal stresses, and those stresses will tell you where the cracks will be most likely damaging, where they will be most dangerous for the component. So I did such a simulation, which only handled making that component a bit simpler because I found it a bit too complex. So I tried to reproduce it, but in a very simple way, because a lot of these complexities I didn't need. But what I did make properly was this so-called stop, which is one of these 4 connectors between the door and the fuselage. And the reason why everything happens here is quite logical, because all the boundary conditions are effectively applied through the center of that stop, which you see maybe better here on the right-hand side. So the center here is where you bolt that thing to the fuselage. So this is what prevents it from leaving, really, the aircraft and starting to fly away. So how do you deal with that? Well, the problem was that you imagine that you have a crack here. And if you look at that representation on the left, which is a part of that humongous stop, which is this part here, which you see here as well, meshed in much more detail. Well, that component here is where the cracks are assumed to be, because this is where the stresses are highest, right? So the loading on that is effectively the negative atmospheric pressure, because you pressurize inside the aircraft, which means that you have an internal pressure pushing towards the outside, and the pressure inside the aircraft is trying to push that thing out of the aircraft. This is why if you open that door during a flight, everybody would be sucked out of the aircraft, because the pressure inside is higher than the pressure outside. Why is it higher? Because at 30,000 feet, 10,000 meters, the pressure is much lower than it is on the ground. And in order to breathe, you have to be under approximately the atmospheric pressure. 9 psi is a bit less than the atmospheric pressure, which is also why if you go on a flight, you tend to swell because the pressure inside the aircraft is a bit less than the pressure you're used to. That's why if you have certain conditions like heart failure or problems with your capillaries, you need to be careful when you are in slight depression, under pressure. I mean, under meaning less pressure. Right, so you have a loading, it gets transferred, and then you have these cracks, they start, let's say here. So the way you do it in these norms is that you insert an artificial crack at the worst possible place. And I computed that this was the worst possible place. So what I did is I put a crack there. But if you look at the mesh, I mean, immediately you realize a problem because, well, first of all, I need to know in advance where the highest stress location will be in order to put the crack there. And once I know that, not only this, but I also need to refine the discretization, use a lot more of these triangular elements, you know, these tetrahedral elements that you see here. I need a lot more of there because we already talked about it in class. When you have a crack, you have a discontinuity, but you also have a singularity, meaning that the stresses go to infinity at the tip of the crack. I'll come back to that. That means that in order to capture that solution, which is, let's say, singular, in order to capture that, you need an infinite number of polynomial functions because that does not converge. You know, polynomials do not converge to non-defined functions like 1 over root r, right? So there is no convergence. If there is no convergence, you can increase the order of the polynomial as much as you like, and that's going to have absolutely no effect. So the question is, how do I know where I should use more of these elements? And how do I know where I should not use more of these elements? In other words, what is the criterion that I'm supposed to be using in order to decide what to do? So that is the question that I asked myself, because as a PhD student, I had not yet understood that there was a problem about the a posteriori error estimate. So what is the quality of the simulation? But very quickly I realized that all I was doing was very limited because I was initiating the crack here and the crack would grow. It will grow approximately in the plane, which means in that plane here, because the load was approximately tensile. So it would open the crack and it would grow. So I was lucky because I put enough elements along that plane, which you also see here and there. But the problem is, in reality, I cannot know in advance where the crack is going to grow, right? Otherwise, if I knew, there would be little need to compute anything. So that is, in fact, what everybody was doing before we did this work. People were computing the growth using extremely simple solutions, which were not even using finite elements. They were using some very simplified methods using codes developed at NASA called NASGRO and AVGRO. So these codes look at the propagation of a crack in a plane, assuming the worst possible tensile load and assuming there is nothing around. So there is no other structure. So it's the worst possible case, because if you have more stiffness around, the rest of the stiffness will prevent the crack from growing. It will somehow control the growth. But if you have nothing around, there is no inertia, let's say, to prevent the crack from growing. It's not exactly inertia. It's a bit of a fake comparison, but you get the gist of it, right? If you can constrain the crack because you have more structure around, it's going to be able to redistribute the load. But here you assume everything happens in a plane, and therefore there is no redistribution of the loads. Therefore, the case is really worse. So that's what we try to improve. And we did to some extent, but I was very dissatisfied with these results because what I realized is that I could absolutely not predict where the crack would grow, and therefore I would need to know in advance where things were. And that is really not intellectually satisfying. You would like to have a way to refine the mesh as the crack grows. And this is what we developed over the subsequent, I would say, approximately 8 years after my PhD. I applied for several grants in the UK, and then in Glasgow, then in Cardiff, then in Luxembourg, to continue that work, which we did with Senairo in Belgium here, not far away in Gosselies, close to Charleroi Airport. And this is a very active aeronautical area in Europe. And so we developed a method to compute the a posteriori error, and I'll talk about that later, because it's a very interesting approach, right? And we were the first to do that, which was actually very nice. But now what I'm going to tell you about is why we even need to refine this mesh, and why there is even a problem when you look at fracture. So now let's rewind a little bit. Let's forget what I just said about a posteriori errors. Let's just figure out, how do we take care of a crack in a complex geometry like this? So in order to understand that, we need to understand what a crack is. And the reason why I talk about cracks is not because I think this is so critical for everyday life, although personally, I'm really in love with that topic. I find it very interesting, but because it's a good mathematical case, which is almost equivalent to many practical cases you will see in real life. And I will talk about those a bit later. It could be multi-fluid flow, for example. You could have two-phase fluids, one phase on one side, one phase on the other, or gases. You could have two media that are separated by a discontinuity. That could be two materials. For instance, you could have two types of steel grains on top and bottom. You could also have bacteria growing, or cancerous cells that are growing, or anything that contains two phases or an interface. So any problem where you have an interface between two materials, it could be, for instance, fluid flow, free surface flow, and so on. Every time you have that, you will need to handle some sort of discontinuity. And a crack is simply one case of discontinuity. And what I also like about it, as an example mathematically, is that not only does it have discontinuities, but it also has singularities, meaning large gradients at the end of the crack. So in 2D, a crack is a line. This is what you see here. This is a set of dimension 0, meaning that it is a perfectly perfect line. And that line doesn't have any thickness. And across that line, what you're going to see is a discontinuity. That means, again, if you are a little ant that's moving around, as the little ant crosses the crack, which is here noted as gamma 0c, as the ant crosses that thing, well, you have to handle a discontinuity. And that discontinuity is the problem that your finite element solution needs to handle. On that schematic here, you have two notions that we talked about in the theory part of that course. This is also theory, but a little bit easier to deal with. You have gamma u, which is the Dirichlet condition. This is where you fix the unknown u. And you have gamma t. Gamma t is the Neumann boundary condition. Okay, so what does that mean? Now you have on top of that the surface of the crack, gamma c 0 at time 0, and you have possibly some part of the crack on which you impose some force. And that would, for instance, happen if you have case of concrete. So in concrete, you have aggregates right? So the aggregates are these stones and sand and cement. So they sometimes bridge the crack. So the crack would be two faces like this, so here, and in between some aggregates would be locked in. And those would help transfer the load, which would otherwise not be transferred between two surfaces that are distant from each other. But if an aggregate makes a bridge, or fiber makes a bridge, if it is these polymeric fiber reinforced polymers, then you're going to end up with a situation where there is some sort of traction or fracture force that is being transferred across the crack. And that's what I like. You have discontinuities and singularities in the same problem, which make it twice as hard to solve as anything else. So this is why we are interested in this partition of unity method. And once again, what I'm saying here is not only valid for cracks, it's valid for anything that handles discontinuities. For instance, you could imagine the top case could be anything. This one here could be two ice cubes growing, not cubes actually, ice disks growing to become one. So these surfaces have to merge and they have to become only one line. And the top cases here, you see the generic approach where the mesh, which is these little triangles, follow the discontinuity. So the mesh actually follows that line here in the middle and on the right. And on the bottom case, you see the partition of unity approach, where the discontinuity, so that line that is growing, does not need to be meshed explicitly. As you can see, the line that is growing, different colors, is growing through the elements. The elements are split, they are cut by the line. Same on the right-hand side, bottom. You see the crack is growing, but the crack is growing independently of the underlying mesh. So that is actually very exciting, because if you compare to the top case, you see this little dot that's moving, that's the crack tip. And you see this little flower around the crack tip. That is there in order to capture the singularity and the discontinuity, but mostly the singularity, right? So very important to see the difference between the top and the bottom case. At the top, all the elements are conforming to everything. Every time you get a new crack advance, what happens? Well, you get a new type of element. You need to regenerate the mesh every single time step. Maybe not the whole mesh, but at least a large part of that mesh. And the bottom case is completely different. Now you can incorporate the crack in the geometry without needing to change anything about the mesh. Okay, so the question you probably ask yourself is that this sounds a bit magical, and how do we make that happen? And that is what we're going to learn today. Okay, so here are a little bit of revisions on what is partition of unity. All right, so I'll start by telling you once again, because we looked at it in detail at the beginning of the course, what is Sea's lemma. So the idea is that if you try to capture a solution, the solution lies in a certain space. So the solution, the exact solution, will be called U at the top. And what we're trying to do is we're trying to see how well we can approximate U using a finite element approximation of U. And the finite element approximation we call UH, U sub H. What we try to find is the difference between the exact U and the approximate U called UH. This is measured in some norm. A norm is effectively a distance, not exactly, but it measures how far things are from each other. Norm of a vector, you're familiar with that, is the length of that vector. So here we look at the length of the difference between the exact and approximate solution. And we are able, thanks to Sea's work, to bound it, meaning to find an upper bound, something to which this difference is always smaller, which is in essence equal to V, meaning any function of the exact solution space, minus the interpolation of U, which is what the finite element solution is trying to do. Also measured in the same norm. And in the same way, if you measure the error in that norm, H1, you will see that it's always less than some constant times the size of the mesh H times the norm of the exact solution in H2. So every time we add, even if you don't understand what H1, H2 mean, it means that we try to differentiate that function twice. So every time we add here a number, it makes that norm higher. Okay, that's the way to think about it. Why is it higher? Because if you compute only the norm of a function, you will get some value. Now you look at the derivative of that function. By definition, the derivative of the function is not as smooth. So when you compute the norm of that, you effectively measure the smoothness. If you compute the H1 norm, you measure the smoothness of the function plus that of the derivative, because you integrate the derivative. If you measure in H2, you integrate the second derivative. So the higher you get, the worse it becomes. And so what you say is that the error that you compute is always less than some coefficient times the mesh size to some power, we'll see that later, times the norm of U in some higher norm. Okay, and there are some things of which that C depends, such as the physical constants, the geometry, quality of the elements, and the degree of the polynomial approximation. And so now, how can we, in general, now this is the absolutely most general case, we already looked at it in class, but I really want to do it again, because I think it's, first of all, not easy to understand the first time, and it's the basis for so many questions that you're going to ask yourself in practice that I really think that we ought to spend more time on this as opposed to less. And if there is anything you do not understand, please let me know. I'll be very happy to go more in depth. Because that really tells you what the limits are of standard finite element approximations. And I'm talking finite elements, but you can understand that as finite difference too, because finite differences we saw also in class is equivalent to finite elements in the case, at least, of a regular stencil. So what do we see? We see that we have an a priori error estimate. What does that mean? Why am I even interested in all that stuff? Okay, let me go back and tell you why I'm interested. So here I told you there is a singularity. That means the solution is not smooth. It is rough, right? Solution is very rough. It means it's infinite here, or maybe its derivative is infinite, but whatever, it's not smooth. Then now you have a jump here. So do you think that's smooth? No, that's not smooth. A jump is definitely not smooth. That's a step, like a staircase. And so I'm dealing with all these cases. And what I want is to know, let's say I use a finite element method with linear polynomials or quadratic, cubic, whatever. I'm using that. So that is what is written here. The P, that's the polynomial order. For now, forget the rest of the equation. We'll come back to that slowly. So we have that. That's the polynomial order. And let's say that the mesh size is H. That means that the largest element in the mesh is of size H. If it's a regular mesh, it's just the size of the element. And now let's look at what is tricky to understand. Once again, this is this norm. So I'm going to repeat that once more, because for your project, that's going to come in very handy to understand that. You very rightly asked me, how are we evaluated, which is always the million-dollar question when you take any course, isn't it? And so how are you evaluated? So you are evaluated, I told you in detail in the signal group, so I'm not going to repeat that, but at least I'm going to tell you one thing, which I talked about. I talked about verification and convergence analysis, convergence rates of the method. So I will come back to that, because in the case that I'm talking about, those are partial differential equations that you're solving. There is always a way to know how fast the method converges. In the case of agent-based methods, it's a bit different. But Professor Vincenot, Christian explained that to you. How do you know if your method is actually correct or not? So you will have to do that in order to convince the reader that the work you've done makes any sort of sense. Why? Because there are some methods that if you use more elements or more points, the solution does not go down in terms of error, but up. So why would that be even useful in any way to anyone? Because you want to be sure that as you refine the mesh, your error level will not go up, but it will go down because you use more energy, more compute power, you warm up the planet more. So you don't want to warm up the planet to get a worse solution. That makes no sense. You'd like to have a better solution. Fortunately, this is why finite elements are the most widely used method by far compared to any other method. I mean, it's really like the panacea. It can solve almost everything. And why is that? I mean, of course, finite volumes, discontinuous Galerkin, for fluid flow problems where you have conservation laws, that's a different story. They are also very much used, especially in very high accuracy cases where you cannot afford to make any mistake, because finite elements do not conserve mass or volume exactly. They conserve mass and volume approximately on average because of what I said in the lecture last time, that you use an integral sign. That means that you integrate everything, makes things easier because you decrease the continuity requirement, but also leads you to having an average solution, not a pointwise solution. So it makes things more stable at the cost of being exact. It's not exact anymore in terms of volume, mass, momentum conservation. It's only average. On average, in the element, you preserve what you want to preserve, but not exactly, not pointwise, contrary to collocation methods, or methods such as finite volume methods, where you in fact write the conservation law actually in actual fact itself. Discontinuous Galerkin methods, which are generalizations of finite volume, they also make sure you have perfect preservation of whatever you're conserving. When I say perfect, I mean machine precision level. And finite elements don't do that. But they are the best methods in terms of mathematical provability. You can prove almost everything. It is extremely well supported by mathematics theorems. You can really rely on that. And what does that mean in our case? Okay, in our case, it means when I say a priori, I mean error estimate. What does that mean? It means I'm computing the error. What's an error? Well, an error is how far I am from the solution, which I don't know. So now you're going to tell me, how in the world are you going to tell me what the error is if you don't know the exact solution? It's like telling me how far I am from the target without knowing the target. How is it possible? It's like, okay, I launched a rocket to the moon, but I don't know where the moon is. How can I know if I landed there? Well, in finite elements, you can. And this is one of the super beautiful things. I mean, I find it completely unbelievable, actually. If you don't know the math behind it, you will find it mesmerizing, because it really means literally, I don't know what I'm looking for, but I can tell you that if I look for it in that way, I will be that far from it. You know, it's like you're doing an obstacle course, orienteering course. You're trying to find a place. You don't know where the place is, but you know that using a certain orientation method, you will get at maximum 100 meters away from the target. That's what it means. So that's super powerful stuff. And it doesn't look like that, but it's very, very impressive. Because what that very fancy equation, which I can admit is very fancy, it's intriguing, and it is also intimidating to everyone, to me as well. Every time I see it, I'm completely awed. So what is there? You have an h, that's the mesh size. You have a polynomial order, that's the polynomial approximation degree. And then you have a bunch of stuff like m. So m is the norm in which you measure your error. So let's say that I'm interested only in the error on the quantity I'm calculating. If I'm computing temperature, I'm interested in the error in temperature. So I just do temperature minus temperature approximate, and I compute the norm, the m norm. So the m norm in that case is the 2 norm, not H2, but L2 norm. So that means I'm computing the sum of the squares of the differences between the exact temperature and the approximate temperature. All right. I could also decide to compute the error in terms of the gradient of temperature. In that case, I would not be adding only the difference between T exact minus T approximate, but also grad T minus grad T approximate. And logically, you expect that norm to be higher than the norm dealing only with the temperature T, because you add another term, first of all, and because the difference in gradients will be more than the difference in temperature itself, because the higher the derivative you compute, the less accurate the solution will be. That's sort of obvious, right? Because the more derivatives you take, you can take examples from any function you like, except harmonic functions, because they will be always infinitely differentiable. But any function which is not infinitely differentiable, the more you differentiate it, the more jumpy it becomes. And that's exactly what you're looking for here. So let's say that we measure it in some easy norm, let's say the L2 norm. So here on the right, what we're going to have is the minimum of the polynomial order minus that number. In that case, let's say we can take just 0 to make it simple. We just take m equals 0, right? Because it doesn't really matter at all. So what we have is the minimum of the polynomial order plus 1 and r. So what the hell is r? So r is the regularity of the solution u. That means how many times can I differentiate u and compute the integral of that differentiation value and find something which is still well behaved. So for example, if you have a polynomial of order 5, you can differentiate it infinitely and you will still have continuous functions. But if you have something like a Heaviside function, you cannot differentiate it at all. If you have a function like that, you cannot differentiate it either. Not at 0, absolute value of x, for example. So that measures how rough the solution is. So what does this exponent here mean? Well, you have the h. The h is the mesh size. That thing is going to go to 0. And you would like that right-hand side to go to 0 as fast as possible, because if it goes to 0 fast, it means that the error on the left will be stuck between 0 on the left and something on the right, which will be very, very close to 0 and getting there very fast. So you want that thing on the right to go 0 to 0 pretty fast. So what can you do? Well, first idea, I increase the polynomial order, right? Because let's say that h is anyway going to 0. So let's forget h. Now let's say I increase the polynomial order. What happens? Well, I mean, I have this min here, which is really annoying, because even if I increase p, I'll be still governed by this r. So everything will be governed by the regularity of that solution. If the regularity is low, meaning r is low, meaning the HR norm that I can compute of u is very small, let's say only L2, for example, then I'm going to be totally lost, because we can have here p equals 10. We will have just a higher number here, but that number will limit everything. So in other words, the approximability of the solution depends heavily on the regularity of that solution. So if we want to do better, what can we do? And that is the idea that Babushka had in 1994 with Melenk. Markus Melenk, who is now in Austria professor. They came up with this fantastic idea to say the final element approximation is as good as the worst interpolant. As good as the worst interpolant. So that means you can increase that p as much as you like. That really doesn't matter at all, because if your r here leads to an infinite value, well, you're done. You can do whatever you like. It will simply not change anything anymore. So this is what I say here. If m equals 1, r is small, meaning that you cannot compute many derivatives of u, you end up with the following. Replacing m by 1, r by small, you end up with ch to the power min of p plus 1 minus 1, which is p, and r minus 1, which is r minus 1. Effectively, that guy here is going to be governed by r minus 1. R minus 1 is small, so it's going to be the one governing here. And on top of that, if you followed my argument about the hx norms, if r is small, hr is large, because you are going to have a hard time computing the derivatives of u. Understood? You will have a hard time because the derivatives of u will be very badly behaved. So when you compute the integral of, let's say, grad u squared, that's going to be a large number. You don't want large numbers here, because that will be a coefficient in front of the h, which will really be a pain. Because the larger this value, the higher the curve will be in terms of error. So the higher the convergence slope will start, let's say. So now you have two parts in that convergence. You have the h to the power whatever, and that power gives you the convergence rate. And that's what I want you in your project to figure out for your method. I want you to figure out what is the convergence rate of the method you're using. So I want you to decrease h, compute the error, decrease h again, compute the error, decrease h again, compute the error, and do that all at least 3 times, if possible 5, 7. Definitely not 2, because that, 2 points give a line in any case. And you need to see that as h goes to 0, you will go to 0 at a certain rate, and that will give you this exponent here. And then you will compare what you compute, which is a posteriori, to what you know from theory, which is a priori. So a priori estimate gives you the slope that you expect on that convergence curve. The convergence curve will have in the y-axis the error level. In the x-axis, it will have the mesh size or the discretization size, whatever method you're using. Now you will have a slope of that curve, and that will give you the exponent that's here, which you will compare to the theoretical exponent. And you can do that for different values of p, for different values of whatever the parameters of your solution scheme are. And then the height of that curve, so not the slope is governed by this power, right? It tells you how far you're going. You're in log plot, by the way, how fast you're going to 0. Well, but the height, as I'm showing here on the screen with my hand, is governed by the constant which is there, which you don't know, and the norm of that u, which you also don't know, you cannot compute usually. That's not computable. That's what, well, because you don't know the exact solution, so you cannot compute that. But it's going to be given not the slope, but the height. So the smaller these values, c times norm of u, the smaller it is, the lower the curve will be, or the line, which means that the error will be less. If you have a very large norm of u, then you'll start high, right? So same slope, but you will start at a higher error level, meaning you will need more elements to get to a certain error that you require. Okay, so that's it. So that's very interesting. At least I think so. So how are we going to deal with that stuff if we do not do anything? So as we saw, everything is governed by u. U is that exact solution whose norm we're looking for. Okay, so we know that that norm is maybe not very regular. The function is not very regular. So in that case, we know for fracture, for example, that we cannot integrate the derivative. In fact, we cannot even compute the derivative at 0. And so people came up with tricks to make finite elements work, which is one of them is shown here, and that is invented by Barzoum in 1974, which effectively creates an artificial singularity at the tip of the crack. Very smart, but requires this rosette to move around, as I showed on a few slides before. Here, you see at the top, you have this rosette moving around, which is supposed to explain what is going on with the cracks as it's growing, okay? All right. So what else can you do, which would not require having these things? Well, you can do very nice tricks. And I'm going to actually not talk about this because this is too fracture related. I want to be generic. Okay. So now we just concluded that if we use finite elements, we may increase the polynomial order, and that will be absolutely pointless. Right? I hope that's clear, and I convinced you of that using that equation. And so, next question. Obviously, we want to solve these problems. We just don't want to not be able to solve them. So how do we do that? Well, that's the question that we are now going to try to address. What we want to do is solve problems where you have discontinuities, singularities, large gradients, boundary layers. Boundary layers, you know what that is. If you have a cylinder in a flow, for example, close to the wall, you will have very large values and functions that go to infinity. So that is something which is akin to what happens in singular cases. Same thing in Helmholtz equations, electromagnetics, you will have these cases as well, and you need to know how to handle them. Oscillatory behavior is also a cool one, because if you have very high frequency oscillations and you have only low order polynomials, well, you will never capture these oscillations. So then you need other approaches like Fourier analysis or similar. And the next really important component or ingredient in what I want you to capture today is what we do in order to solve that issue of not having the proper functions in the approximation space. What we do is extremely simple. As Babushka said, the error comes from the fact we don't have the approximant that we need. The exact solution looks like square root of r, sine omega t, exponential minus alpha x squared, with a large alpha, for example. Well, all these functions are not in the space that the finite elements span, because the finite elements span only polynomial spaces. 1x, x squared, xy, y squared, xyz, x squared, yz, x, y squared, z, x squared, y squared, z squared, whatever you like, but only products of monomials, right? That's not very nice, because sometimes that's not what we like. So what we try to do is we want to reduce the error, not only locally, but also globally, meaning over the whole domain, and we want to improve the convergence rate. Now the question is, how can we do that in a very practical way? Let's go. First question, how do we deal with discontinuities? And second questions, how do we classify even discontinuities? So the first type of discontinuity, very easy, are called strong discontinuities. They are strong because the function itself is discontinuous. Example, crack. You move here, your little ant, and suddenly you need to jump down the cliff to be able to continue on the function. That's a jump. Weak discontinuity. The function itself has no jump. As an ant, you can climb here and continue, nothing will stop you. But if you try to do that on a derivative of that function, you will end up in the top case, which is a discontinuous case. So the first derivative is discontinuous at that kink point here. You don't want that. Example, material interface between two domains. If you have two materials that don't have the same properties, you will have that case here, meaning that you will have a different level of strain, which is the gradient here. The slope will be different, but the same level of stress. Otherwise, there will be no continuity, at least for general interfaces. There exist interfaces which transfer stress in an imperfect way, but that is very technical, and this is not something we discuss here. Now, second question is, how do we actually enrich? Do we enrich globally or do we enrich locally? What does that mean? So the first idea, which came from Strang and Fix in 1971, is to enrich the whole domain with one function. So the whole domain will be enriched, and we will hope to capture the solution by a global enrichment. So obviously, I think everybody is able to figure out what is wrong with that approach. At least I hope so. Maybe I give you a few moments to think before I tell you what's wrong with it. It's always better not to be told, but to figure things out on your own. So I'll let you think. I don't necessarily need you to tell me what you're thinking, but at least to think on your own, for yourself, for a few seconds. Let's say we enrich everything. What is going to happen? What are the disadvantages? What are the advantages? Okay, let's say that you try to think about it, and we'll see later if you are right or wrong. Now, local enrichment. So local enrichment means that you are only enriching locally around features of interest. If you have a crack tip, the end of a crack, you only enrich around that tip. Now, if you have another crack tip in the same domain, you only enrich around that tip, and then that tip, and so on and so forth. So that's super cool, because you can have several enrichments everywhere, different, and you can handle different types of features that you are interested in. So now I'm going to introduce how in practice, and I usually don't do that on slides, but these slides I've prepared over many, many years, meaning 19 years, and I think they are pretty good. And I would like to be able to spend the required amount of time on each slide so that you understand everything. And on top of that, I'm also continuing the class notes, which will be a book at the end of the semester, hopefully, that you will be able to use as a reference, I hope. And by the way, too, we wrote a book on this, which is called Partition of Unity Methods, with Sundararajan Natarajan and Alexander Menk, who are two of my PhD students, the first two, actually, that finished in 2011 and 12. So you can find it in the library, and you can, it's Wiley, the publisher, the editor. And there we go through the whole history of why things have happened in what way. We have very clear tables, we have code, we have open source pieces of software and so on, which are also available online, which you can find there. I'm not saying you should read the whole book because it's probably 400 pages, so it's a bit of a lot of work for only one method. But honestly speaking, I think it's a good account of recent changes in the landscape in terms of numerical methods. So I wouldn't say that everything is useful, but I would say that the first 5 chapters or maybe 4 chapters will be extremely useful to understand anything in terms of numerics, because it's not only focused on that. Okay, end of parentheses. What we do for partition of unity is the following. We select a set of functions, and we call them phi I. Until now, we call them ni, maybe. And these i's should be uppercase, not smaller case, but they are here written very clearly. So what you do is you select a set of functions such that their sum is 1. If you paid attention in the previous lectures, you know that the finite element shape functions are exactly that. They are shape functions that sum to 1. Why? Well, if you follow my mouse on the screen, you see that if I take, let's take that case here. So I put my mouse on the x-axis, I move up, and that gives me the value of n2. That's this little small thing. And then I look at the value of n1. That's the little big thing. If I add this little small thing, bottom part of the triangle, to this bigger thing, I get 1. So that line plus that line is equal exactly to 1. And that is called nothing else but partition of unity. You can check it. X2 minus x divided by x2 minus 1 plus x minus x1 divided by x2 minus 1. If you add these two, you end up with x2 minus 1 minus x1 because the x drops out, and you end up with 1 over 1, which is 1. So that works. n1 plus n2 equals 1. Cool. Now, what does that actually tell us? It tells us that thing. Any function p you can multiply by that so-called partition of unity. Sum over I of phi I equals 1. Multiply that by p, you end up sum over I of phi I times p equals P. Easy, right? And now that's cool. It means that you can now reproduce any function using that set of partition of unity functions. How do I do that? Very easy. Now you can adjust the parameters associated with phi I that we call qi. Those parameters you can adjust in order to fit a function p of x. And we'll see exactly what that means. In effect, it means that if you choose p of x on the right and qi is equal to 1, then you reproduce exactly sum over I of p of x times 1 equals p of x. So that's exactly what you like. So that's cool, first of all. And now let's see if we formulated that in a finite element sense, what would that actually mean? Okay, so last time we did that, but for the standard finite element method. Now we're going to do it for the partition of unity enriched finite element method. So let's assume we have that equation, which we looked at many times. That's a 1D boundary value problem, which means nothing else but Laplace plus a body force. That means Poisson equation. And your boundary conditions are u of 0 is 0 and u of L is UL. Right? So that's the only thing that you know. And based on that, you're trying to solve that equation. That's, in that case, an ordinary differential equation. And as we usually do, using finite elements, we multiply by a test function. The test function is W. And we then integrate over the domain 0 to L. That's what we're doing here. We integrate, and then we integrate by parts. And we end up with that term, dw over dx, du over dx. We already did that many times, so there is nothing new. On the right-hand side, we multiply this w with f. That gives us an inner product. This is a bilinear form, which is the integral from 0 to L of the test function w, or the weight function, times f, which is the body force, or the forced term, the sink, or the source. So then at the end of the day, you end up with a discrete variational problem, and it can be stated like that. Find UH, unknown, finite dimension. Here we are still in infinite dimension. There is no H anywhere. In capital UH, satisfying the boundary conditions, and such that for all WH weight functions in capital WH, which is usually exactly UH, except that the test function vanish on the 0 Dirichlet boundary. So they are homogeneous Dirichlet boundary conditions applied on WH. Well, then the bilinear form applied WH and UH should be equal to the inner product WH and F. Okay. And now what we're going to do is we're going to say, right, so this WH and this UH, I'm going to use the Bobnov-Galyarkin approximation. So Bobnov means same approximation for UH as for WH, and we saw that is fine for elliptic problems. This one is an elliptic problem, unless F is very weird. So we end up here with the following, trying to find an approximation for U, an approximation for W, so trial function U, test function W, such that the left-hand side equals the right-hand side. How does that look? Well, you have the left-hand side, UH of X, which is the standard finite elements part. So that is what you usually would do. You have polynomial functions, Ni, can be these little hat functions, times ui. And these UIs, they are the coefficients at the nodes that you're going to solve for. So you will end up with a vector, and these UIs will be some of the unknowns in that vector. But then you have now another path, which is called sum over j of the functions we had chosen, the partition of unity, times the function you want to reproduce, psi, times qj. Psi can be discontinuous, discontinuous derivative, singular solution, cosine wave, sine wave, Bessel's function, whatever you like. You can just put it there and it will be exactly reproduced. Why will it be exactly reproduced? Well, let's take an example. Let's say that UIs are all 0. That goes to 0. And let's say that all the QJs are 1. Well, then you have sum of phi j times 1 times 1 times psi. Sum of phi j is 1 times psi gives you psi. Right? So that means that you are exactly able to reproduce psi. That means you can find these UIs and QJ, I just found them for you, such that the function psi is exactly equal to u at h at any point x. So you can exactly reproduce it everywhere on the domain where you enrich. So that's an exceptionally cool property. And now let's pass on that by choosing WH equals the variation, because that's only got to do with mechanics, and at the moment we don't really care about that. What we end up with is a matrix vector equation where you have a so-called stiffness matrix, which has 4 parts. I would like you to maybe think about what that means and why it is like that. So this SS, SE, EE, ES. So that's standard, only that part, the blue part. Then standard enriched will be blue part multiplied by enriched part, enriched standard, and then enriched, right? Between this and this itself. And you have now unknowns. Normally you would have only US because you have only the standard part, but now you have extra unknowns that look like QE. And then the right-hand side has a force or right-hand side vector standard part plus another one that's the enriched part. So I hope that that makes sense. Okay. Now, how do you compute those terms? You compute them exactly like that. So you can take a look. It's pretty simple. You will have the derivative of the standard function ni times the derivative of the standard function nj, and that will give you that term. And then you have all the other terms. Standard function dni times derivative of the enrichment part. That gives you this mixed term. The symmetric version is here. And then you have this EE term, which is enriched, where you have the derivatives only of the enriched part, which you see here, the red part. And same for the right-hand side vector, which is pretty much identical to the other one. I hope that's clear. If it's not, let me know. Okay, so all that I already said. And in the literature, you can find a huge amount of different naming conventions. So the first person to come up with that is Markus Melenk and Ivo Babushka. Babushka passed away a few years ago, unfortunately. And then Duarte and Oden, and then Belichko and Black. So you have essentially these 6 names, and they come around all the time. In fact, Melenk and Babushka is 96, but 94, there was the first paper. Then you have also Strouboulis on the generalized finite element method. So lots and lots of papers. That's why we wrote the book, because it was becoming a little difficult to follow the literature. And so we thought it's very useful to do something a little bit, let's say, simpler and more constructed. Right. So now if we take the example of fracture, so crack, what is going to happen now? Well, you're going to have this function UH of X. That's the one you see here. And that thing is going to be approximated by 3 terms that you see. The first one is the standard part. That's the standard polynomial function, ni of x times ui, right? Okay, very simple, just standard part. Second point is going to be the discontinuous enrichment. So that is going to give you a jump in the function. So that jump you see at the bottom left here, this is literally a discontinuous function, heaviside function you use directly in the approximation. And then that discontinuous function you see here, it is going to have to do with these circled nodes. All the nodes whose support is cut by the crack will be enriched with that jump function, which means now you will have to integrate a discontinuous function, which leads to other problems. I already told you, I think everywhere in life, there is no such thing as a free lunch. If you win something, you must lose on another front. That is usually the case. You rarely win on all fronts at once. So if that method solves an issue, it probably creates another one. And that is exactly what's going on here. In fact, it creates a lot of other issues, but it still makes the method super useful. Then you have this third part, which is the singular tip enrichment, and it looks like exactly like that. So sum of nk times that guy here. That looks a little bit weird because you have 4 functions, but you can forget that it looks like another sum. It just remember that that comes from the asymptotics at the crack tip. So what that does is, if you know how the solution looks like asymptotically, meaning at r is equal to 0, well, what you can do is you can take these asymptotic terms, these 4 functions, they span the space of solutions close to the crack tip. So they span the exact solution. So you know, because you can compute certain things by hand, that these 4 functions are essential to capture the exact solution close to the tip. So what you're going to simply do is add them to the approximation. So here, we just added that in a compact form using this summation convention, meaning that we have 4 functions f alpha, which are the following: this one, that one, this one, and that one. So these 4 functions are here. But you could also imagine writing it 4 times the sum here with each function f1, f2, f3, f4 with different coefficients b's. So there is nothing really supernatural about that. Now, if you look at these approximate solutions, which come from knowledge about the exact solution, that's what you see here. That looks very much like a square root. That is the first function, root r sine theta over 2. Looks like that. Second function, root r cosine theta over 2. And so on, sine theta over 2 sine theta, and cosine theta over 2 sine theta. All right. So I suppose then I'm going to now tell you what happens if you do that enrichment out of the box. So let's say that you have a crack and you have a mesh. The crack tip is here. You look for the elements to enrich. So we look for all the nodes such that their support contains the crack tip. What is the first one? That one. That node, the bluish thing, contains the crack tip. And that guy here contains also the crack tip. right? You now, what happens next? Is there any other node? Yeah, that one. Anyone else? Yeah, this one. Okay. So, is there any other one? No. All right. So then what do we do? Well, now we look at these four. And we compute the solution. And that's very important because we're going to now compute the rate. All right. Rate of convergence. What does that mean? Well, let's say that we refine the mesh. So you see here, that area is enriched, right? That area here contains knowledge about these functions that I just talked about, right? Right? So now what do? We refine. Boom. The area decreases. We refine. Again, the area will decrease again. So what does that mean if you compare that image to this image? It means that here, the role of enrichment is all that area compared to that big area of the domain, right? So the gray domain is the total area. And this is the smaller domain is the enriched area. But in that case, when you refine the mesh, you see that the enriched domain is even smaller relative to the gray non-enriched domain. Is that right or not? Yes, of course it's right, because it's approximately half the size, maybe a quarter even. If we refine it by a factor of 2, the mesh, then that area is refined by a factor of 4. So what does that mean? If we keep refining, well, the area here that's enriched, therefore touched by the enrichment, is going to go to 0. Not cool, not nice. Because if it goes to 0, it means that its influence on the result is also going to 0, which means that in your convergence rate, although you expect an optimal convergence, you will not get an optimal convergence. And just to tell you that this is not trivial stuff, people didn't think about it at the beginning. They published papers from 1999, 2000, 2001, 2002, 3, and so on, without even realizing that this was the case. And only in 2004 did people start to figure out, oh my goodness, this is a problem now. This is not working. We need to do something. So it took about 5 years for people to, maybe even 10 years from the first paper, for people to realize that that didn't work out of the box. You need to do something. And what is the something? Where this is becoming a little technical maybe. Well, but it's quite trivial. You enrich an area which does not depend on the mesh size. This way, the area that you enrich, or the volume, is going to remain constant. And when you refine the mesh, all you do is you take into account more nodes. That's what you see here on that beautiful graph, right? So now you are in a case where on the left, you refine few nodes. On the right, you refine more nodes. And that allows to preserve the optimal convergence rate. But guess what? You know, it's like Murphy's law. If you solve a problem, then you get another one back. This is not actually Murphy's law. It's what I called conservation of difficulty. You cannot fix a problem without creating another one. It's like really conservation laws. Difficulty will remain one way or another. You just need to weigh your odds and decide what is more negative or more positive to you for this particular case. So finding what is going to go wrong now is even harder than before. So I don't expect you to guess that. But maybe you can actually, if you know a bit of linear algebra, you can maybe imagine that all these little nodes, all these little dots, they are now associated with functions that you add, root r, sine theta over 2, and so on. So those little nice functions, they live everywhere for all those nodes here. So you can imagine perhaps that you will have some level of linear dependence. What may very well happen is that the functions you add are not linearly independent once you multiply them by the finite element shape functions, and you end up with singular matrices. And that's precisely what started happening. And people looked at the method and said, oh no, I fixed one problem, now I have a new one. I need to get rid of this problem associated with the condition number because I cannot even solve the problem anymore. The condition number is so bad. And loads of people, including people in my team, Kostas Agathos, at the time he was at ETH, and then at Luxembourg, then in Exeter, and now he's in industry in Switzerland, working for a startup, and he came up with a way to compute these matrices without having these problems by simply orthogonalizing the enrichment functions together. That leads, using Gram-Schmidt orthogonalization, which is very well known, to a set of functions which are mutually orthogonal and therefore which will not create singular matrices. Very cool method. And there are really a lot and a lot and a lot of methods. The original ones are from Béchet and then from Menck, but we talked about them in the book. And here I'm not going to talk about that because it's definitely too detailed for the level that we are trying to reach. Now, a question that would logically arise here is, what do we do when we wish to make sure that the error that we compute is controlled? So I'm showing you here a bunch of calculations where the crack is propagating. So you see at the bottom left, a crack is propagating in that spanner. At the top, you already saw that before. And on the right-hand side, you see the crack propagating in a concrete beam. And that was done by Kostas, with the initial crack being this penny-shaped crack that you see here. And so now the question is, how do you do that? And funnily enough, I didn't know that 20 or so years later, I would start working on Parkinson's disease with my partner, Anne Grunewald, who is professor at LCSB, because this is Michael J. Fox, and he has a mutation in his, well, he had in his genome, and his foundation is funding work on Parkinson's. And they are based in New York City. And we're going to go there normally next week to talk to these people and to other colleagues at Columbia, because what they are doing is effectively trying to understand where Parkinson is coming from. But okay, that's completely unrelated to what I'm talking about now. But I thought that the face of Michael J. Fox here was quite revealing. But it's nothing to worry about. There are loads of approaches to solve these issues. And you can look at that in the papers, but I really don't want to go into too much detail. What I want to talk about, on the other hand, is how you solve the problem, just to loop back to the beginning of the lecture, how you solve that problem of having no clue where the crack is going to propagate. And when I say the crack, again, I don't want to only talk about fracture here, although, again, I repeat, this is a very exciting topic. And you have here all the papers that we published in the field. I mean, not all of them, but a number of them, and some that others published. What you see, well, you can look at these papers, and you can also download the slides here, by the way. So that's very cool. You can just take that on orbi.uni.lu. It should, unless there was a bug in Orbi, link to these slides. But I will anyway give you the lecture notes. So coming back to that question, let's say that we have an initial crack here and we want to know how it's going to end up hitting that hole. The problem is that you don't know what exactly the crack trajectory is going to be. And you don't want to even know, because by all means, how should you know if you don't know what's going to happen in advance? If you don't know the exact solution, you're not going to be able to predict where the crack actually goes. So the next question is, how do I locally enrich the mesh? How do I locally refine the mesh? How do I choose the enrichment functions? Because, by the way, this is a new way to refine the mesh. Instead of refining the mesh, what you're doing now is you're refining the space. You're not only adding polynomials or adding the number of times you're using these polynomials, but you're adding a completely new function. So it's much more powerful. And this is something that we called E-adaptivity, which is known as enrichment adaptivity, which I think is a pretty cool way to move away from standard HP adaptivity and to be able to finally have an approach which will give you a way that you can, in general, enrich the solution. And this is not so easy, really. This is not so trivial. And it's not trivial because you don't know in advance what the solution would look like. In the case of a crack, and I guess this is your question, if you are following closely what I'm talking about, your question must be, yeah, it's all nice what you're talking about here, Stefan, but unfortunately, in most cases, I have no clue what the actual solution is. So if I don't know anything about the solution, how can I add anything inside that? And that's a very valid comment, because you cannot add something you don't know. And if you knew, you would not need to solve numerically. That's the usual question that you should be asking yourself. And so, if that is so, how do I solve that issue? Well, I thought of the ways that I never implemented, and if you're interested in taking up, I'm interested in helping you along, is to find the type of function automatically based on a first solution. You solve the problem once, look at the error, guess how the singularity looks like, if there is one, or how irregular the solution might look like. So that's a cool thing we never did, and I don't think anybody did, but it would be a nice way to go beyond what we're talking about here. Now, I'm not going to talk about that. I'm going to talk about something much simpler. I'm going to assume we know the enrichment functions. I'm going to assume that these functions are square root of r sine theta over 2, as we saw before. And now I'm going to ask a question. How do we know what is the mesh size that we should use here? What should we use, right? Crack is going to propagate, and we want to know what to use, where and when. So the most stupid way to do it is just to dump as many elements as you can in where you think the crack will propagate and just hope. Which, by the way, is not very convincing either, because you don't know if even modifying that mesh will not modify the crack growth, which we showed in a specific, very unstable case does. And it's very annoying, because then you don't even know if changing the discretization, changing that mesh, is not going to alter the solution so much that you won't be able to actually get the right solution. So you need to be careful with that. And so from the previous idea, which is this, we move to this idea, where, as you can see, the elements are only refined where needed. This is where the crack front is located. And you see you have very small elements, and here, far away, very coarse elements. And we have a few papers with Jean, Pierra, and so on, they are at Senairo, and also with Kostas Agathos that I was mentioning before, and that explain how to do that precisely. So if we summarize what we can, yes, there is a question.
Yeah.
Yeah,
you hear
I'm
me?
listening. Yes.
Yeah. So I had one question. You mentioned that since we don't know the trajectory of the crack to the final big circle that you were showing, and we can enrich that area to be more careful with the crack propagation and try to capture it if we can. So I was just wondering, do we really also know where exactly the crack gonna start with?
No. And excellent question. You know, in my PhD, I told you how I decided that. In practice, we need another model for that. So now this is going more in the modeling of fracture, which is an extremely difficult problem.
Okay, I see. Yeah.
But I can tell you briefly how to do it. I mean, you need a model which is going to, so it is a very deep question that you ask. Because what we are assuming, and I couldn't explain all that because I would need one semester to just cover fracture mechanics. But what you need to know is that the method we use is called linear elastic fracture mechanics, LEFM. That assumes that the cracks are already there. That is a theory by Griffith, which is really 100 years old. And this is what this person thought is the way to go, because they always assumed that you knew where the crack was. And your question was, how long will that structure last? And you just assume the worst case scenario. So that's the crack exists, and it's related to the debonding between atomic planes. And the Griffith crack energy is equal to 2 times the surface energy of each atomic layer multiplied by the area of the crack, 2 gamma A. So this 2 gamma A is the energy that the crack needs to exist. And then what you do is you compute the energy that it needs to grow, which is related to how much it grows and the intensity of the stresses in that region. It's known as the stress intensity factor. This is a whole thing which my PhD advisor was one of the first to be able to compute in a numerical way using domain integrals, which are path independent and which give you a huge amount of accuracy, something I did not talk about today. So that just assumed that everything is linear elastic. So it means that the cracks are supposed to be relatively small with respect to the whole structure. It means that the whole structure remains elastic. It means if I load the structure and unload it, it comes back exactly where it was. There is no such thing as residual deformations. So you do not have a deformation which lingers there after unloading. If you took a piece of rubber band and you elongate it a little bit only, left it back, it would come back to its original position. Now, if you pulled a lot, you would create dislocations, you would create small fractures in the domain, you would then let it go back, and it would not go back its original length because you have residual unrecoverable deformations, which are known as plastic deformations, which you cannot avoid. So in practice, the ways that the crack initiate and grow is by the means of these small cracks, or even worse than that, dislocations in materials such as alloys, steel, aluminum, and so on. If we really wanted to look at that in detail, we would need to go down one scale and figure out, all right, so now what exactly is the state of the material at that lower scale? And then we would need to look at that scale, integrate it over space, and it would give us an average property at the macroscopic scale, and it would allow us to have a way to propagate the cracks. That's one approach. There are many approaches. The other one, which is super in vogue at the moment, which a lot of people want to work on, is called phase field models. And this is a theory that is called also the variational theory of fracture. And that relies effectively on allowing cracks to initiate in the variational formulation. Because if we write the formulation the way we write it now, we don't allow for cracks to initiate. There is no such thing as an energy associated with the existence of these cracks. They are just there a posteriori. We just add them. But as you said, very shrewd remark is that we assume they are there, but we don't know in reality. So there is no way that we can guess this. And this was puzzling a lot of people. And Francfort and Marigot in Paris, I would say approximately 2006, 7, or 8, approximately that time, came up with an approach which is now a model. It's not about the discretization, it's about the modeling of fracture. And they said, okay, well, I don't like this Griffith theory because it does not allow to initiate anything. So I'm simply going to add some sort of integral in there, which takes into account the potential cracks in the whole domain. And I'm going to do, which is crazy, an optimization over all possible initiation of cracks over the whole domain at the same time. Can you imagine? So this is completely crazy because you can initiate cracks everywhere. They can be of any length. They can go any direction. And they formulated a super elegant approach to that. And they even showed that there is gamma convergence, which is something that can be defined to the exact crack when you take the thickness of these pseudo cracks going to 0. So this is an absolutely beautiful approach, which we could talk about if we were to, to work on that. Sharing video animations, you want to include your computer audio while you're sharing? I have no idea. No, I guess. Because there is no audio. So yeah, so that's an example of what you can do if you know initially what the cracks are. So this is one of my PhD students, Dana Sutula, who now works in Munich for Brain Labs, which is a surgical simulation company, and where they look at various problems of how to navigate during surgery. And he was working on silicon wafers during his PhD, and this is essentially a part of what he did just for fun, to show that you can do cracks that propagate and merge, and they change directions, and they interact with each other, and so on. He did that in a very beautiful way. And more than that, he looked at cases where you have hundreds of cracks, I think here 300, and try to figure out how the cracks would move with time, propagate, because he was working during his PhD in collaboration with a company called Soitec SA in France, in Grenoble. And this company was interested in silicon wafers. And what they wanted is to be able to split silicon wafers, which are approximately 1 centimeter in height. So they want to split it here, maybe even less, in order to have a split surface which is as smooth as possible. You don't want any roughness here. And the way you see it here, for example, would perhaps be too rough, because what you do with that surface is then you stick some sort of, you use that for PCB boards, so printed circuit boards, for instance, or to make CPUs or GPUs and so on. So you don't want that thing to be too rough. And the way they created that split is using hydrogen embrittlement, which is nowadays very useful because people try to store hydrogen. At the time, it wasn't a question, but today it is a question. And these people that created Soitec, they came from CEA, which is the atomic energy place in France. And what is super cool about that is that they did not want hydrogen embrittlement in nuclear power plants, because you don't want to make the material brittle. You want to keep it resistant, and you don't want it to break. At least if it breaks, you want it to tell you before it breaks, meaning to be ductile, contrary to what we just talked about. So what they did is that they used that knowledge about materials to come up with a new design approach and fabrication approach for silicon wafer manufacturing and cutting. So what they do is they send at high energy hydrogen ions, or protons, so that they get stuck into the lattice and they create small weaknesses in the material. So these small weaknesses, they will then lead to cracks that are forming. They do some sort of thermal treatment of the silicon wafer. And by increasing the temperature, decreasing it, increasing, decreasing, they create a reassociation of these protons, which are H plus ions, into H2 gas inside these little cracks. And then if you increase the temperature again, that gas is going to expand. And by expanding, is going to push the two lips of the crack away from each other, and it's going to create a propagation. And that's what you see in this movie here. So that's super smart. And that's what we were trying to model, which is super hard. So this PhD was very interesting. And what you see is the roughness after the split. And depending on where you implant the hydrogen, at what depth, you will get different roughnesses. And you would like to know how bad or how good that's going to be. And as you can see, the mesh that we were using is pretty hugely dense. Yep. Okay. So that is exactly what I was telling you 2 minutes ago, which is actually good timing. And I'm not going to be very much longer, okay? Because I know you have other things to do. And for some of you, it's been today 4 hours of lecture. So, but don't worry, you'll be rewarded by suitable ECTS at the end of this course and at the end of your project. So if you're interested in this, there is a super nice book, not book, but let's say review paper, which is written by Nguyen Vinh Phu and another colleague of ours in Australia. Nguyen Vinh Phu was my first master's student. And we wrote together a bunch of papers on what goes around the difficulty that you just asked about. So that was a very circumstantial question. Normally, what you do is you do exactly that. So you have these discontinuities which are sharp, and we just explain why that's a good idea. But we also saw that it's a bad idea because here, look at that mess here. I mean, when you want to simulate that thing, what happens? It's very difficult because you have all sorts of geometrical possibilities. Let's imagine you want to simulate that thing and you want to code that. Right, how far is that crack tip from this crack tip? If that crack tip is less than epsilon from that crack tip, merge. If not, don't merge. And what if another crack tip is also close to this? So you can see all the combinatorial geometrical possibilities that you have. This is horrible, right? And this is 2D. Now imagine that in 3D. Each crack is now a surface. It has a front. The front is a line. Each point on the line needs to decide in what direction it grows. Does it grow 45 degree, 30 degree, up, down, 1 meter length? Fortunately not. Half a meter, 1 millimeter, half a micron, 2 microns, whatever. So you're going to have a field of growth, which is like a manifold on the line. And that thing is going to be for each crack different. And you need to compute that continuously for all cracks, 300 of them. No one did that ever. So not one person was able to solve that problem. And maybe that is because people come up with another approach. And that is exactly the one that you intimated without realizing, which is this phase field approach, which not only solves that issue of having multiple cracks merging and so on, but also allows you to handle the problem related to crack initiation. And this is exactly why Danas and Fu work together, because in the left-hand side case, we have a case where we are using energy minimal XFEM, which is something we came up with, which is supposed to globally minimize the elastic energy. When you decide whether a crack grows, this is actually not so trivial. If I give you two cracks, how can you decide which one should grow? If everything is symmetric, okay, both. But it's never exactly symmetric. So you don't know which one is going to optimally minimize the potential energy, because this is always what the system tries to do. It takes the potential energy, tries to minimize that. How do you do that? But what you do is that you theoretically need to find the optimal way to do that. So you compute the derivative again with respect to all possible directions, and you try to find the one that's going to minimize the energy best. That's the only way. And that's what Danas did for all these 300 cracks. He was computing all the derivatives at each point. If you notice, the crack started on the left, then continued on the right, then started in the middle again, and then continued on the left, and then on the right, and then on the right, and then on the left, and so on. That is a nightmare to deal with. So that's why people came up with this sort of idea of phase field, because you don't need to do all that stuff. And what we did here is to try to compare the, let's say, standard approach, which relies on the global energy minimization, or another criterion, which I'm not explaining because it's useless for now, which is another crack growth criterion. And the other one, which is phase field, to try to compare the crack shape. So you see, the crack shape is not that bad. I mean, we get pretty much the same thing. I mean, we don't get exactly the same thing, but this is a quite difficult problem, so we're not too bothered with that. And then we're able to do that in multiple dimensions. Of course, that looks like 2D, although it is 3D. We're able to look at crack branching, which is also very difficult in the standard approach. Yeah, so that's it. I think then the rest I'm not exactly going to cover now, because it is outside of the realm of what we're discussing. But there is a lot of problems to talk about, and it is partially answering the questions that you just had, which is how to handle crack initiation. This is, as I'm going through the different slides, I'm showing you a little bit what we did later, which was needle insertion in the brain. So how do you decide if the needle gets inserted or not, and how it gets inserted, and how do you simulate that in real time? How do you handle cracks in heterogeneous materials? How do you propagate the error in real time? How do you adapt the mesh in real time, which is what you see on the bottom right? This is the work of one of my postdocs and PhD students, Fouque, who is now working for ANSYS in Lyon. And on the left is Adrien Courtecuisse, who is CNRS now in France. So you can essentially see that these methods of discretization, which are advanced methods, which allow locally to enrich the field and to refine the mesh as we require, and when we require, are extremely potent, and we need to be aware of how they work. We can do that for many possible problems that we could talk about for years to come. But today I'm going to stop, because I think you've had enough of information for the day, especially for those of you who are in the PhD track. And so, if you have questions, by any means, I would be super happy to take them. Maybe not now, because I think everybody is a bit done. At least I am, after quite a lot of interaction with the students today. I would rather start preparing for the next course that I'm giving. And I'll tell you about what happens next week as well. I think we don't need to continue recording. I'll tell you about what happens next week as well, because, as I said, I'm normally in Columbia University, but I've not yet completely, I've not booked anything yet, because there is so much to do that I'm a bit reluctant to making such a trip. In particular, because of teaching, I don't want students to have to, miss courses because of that. So I'm trying to figure out how we could do that. Currently, I'm thinking that some of my team members will probably present what they are working on, so that you can learn from very practical cases. So that for now is the best course of action that I can think of. We have 3, well, more than that, but at least 3 postdocs in the group now that could present. And I think that would be actually very useful. It could give you 3 different approaches to discretization problems, and I think, and mathematical modeling as well for different complex systems. So that's at the moment what I'm thinking of. I will confirm during the course of the week, and you can be sure that I'll do my best to make sure that you have your required amount of information so that you don't get bored. I will also send you the lecture notes as I continue to compile them. And I believe that's about it. So if you have any questions, maybe you can, ask them maybe now. After all, maybe that's the best time. And if not, let me know, but don't hesitate. So any questions on what we covered today? Okay, doesn't seem like it. Doesn't matter, that can be later too. So everything is fine. So fine, and don't hesitate also to DM me if you think that this is the best way to interact. That's also fine by me, as long as we don't lose contact and everything is moving. I'll be super happy to do that in that way. All right. So thanks a lot. Thank you, and apologies to the PhD students for the way that the optimization of the course is done. I was telling one of you just before that a lot of us are in dire situations. We have, in my case, 4 different courses, first year, bachelor, and master's. This is scheduled randomly at random times on random campuses in random rooms, which you can imagine does not make it easy to plan anything, because there is no recurrent day on which there is any meeting possible. For example, tomorrow I have whole day a project meeting with the European Commission to make sure that we get renewed on our funding, and that will last from 8:45 to 7 p.m. And it is absolutely impossible to schedule these things and be sure that we won't have a course at the same time, because the courses are randomly selected. Otherwise, it would be easy to say Wednesday, no course, boom, I scheduled the course on that day. But unfortunately, that doesn't work. So I'm really sorry about that. And I hope that you can forgive us for that, and that you still enjoy what you're learning. And on top of that, that you're learning something useful, and that you're going to use it in your work, in your research, or in whatever else you'll be doing later in the real world. So thanks a lot again. Hope you're doing well, and thank you for your attention. I appreciate it. I really have fun doing that, as you can probably see. That's really my favorite topic among many topics. So I hope you see that, and it's contagious, and that you end up doing anything related to that in your career. That would actually make me super happy. And if you want to get in touch research-wise, do that. And if there are people that can help you in my network, I'll make sure to make that happen. Most likely I cannot solve your problem myself, but I can probably know someone who can. So I hope that this can be helpful, because in total, since the beginning of the team I created, I think I worked with approximately 350 different co-authors. So among these people, I'm sure that someone will be able to help somehow. And so don't hesitate. I'm here for that also, not only to give these lectures, but also to make you, and Christian Vasno is also there for that, to help you connect with the outside world in the most optimal way, in terms of not wasting your time if you have questions in these directions. That goes also for contacts in industry. If you want to find jobs later, for those of you who are already thinking about that, we are also here to help. We worked, I mean, if we take Christian and myself together, probably with over 50 or 60 different companies, as you saw, I gave examples today, but there are 10 times more on the list. So if you like, if you're hardworking and you want to be introduced to someone after I take a look at your project, I'll be very happy to do that. I just need to know how well you work before I do that. Obviously, I cannot just give random people to people that I've been working with for 20 years. So I need to have an idea about what the quality is and your sort of attention to detail and motivation level. But once that is established, then, and I've done that in the past, I can easily introduce you to people that can help you in Luxembourg, but also elsewhere. All right, I think that's enough monologue. So see you soon, have fun, and talk to you somewhere else in the multiverse. Ciao.
Thanks, Professor. Bye-bye.
Thank you very much. Bye-bye.
Bye, thank you.
Bye.
Bye.
Bye-bye.